Okay, so on the test 31 through 38, here's what I'm going to do. We're going to draw a similar figure here. Pretend that goes through there. And I'm going to start out with two slightly different angles than the one I gave, so that you can see the relationships. So I'm going to call this up here 70 degrees, and this one here 100 degrees. So just slightly different. I will, and this one over here, we'll call this one 30 degrees. So those are the three angles that were given there. Everything else can be found from those angles. Let's start here because this is the easy one. If this is 30, this is 150, 30, and 150, right? Let's go over here then. From what we have up there, this angle has to be 30. This angle has to be 30, correct? Because if we're just looking at this line here, the four angles formed around it have to be the same as the four angles up here, because those are parallel lines there. But this angle is divided in two, so this would have been 150 all the way over. This angle has to be 50. Because this whole thing was 150, we subtracted 100 from it. Same thing up here. This whole angle, let me extend that a little bit. This whole angle here had to be 150. Oops, nope, not 150. That one has to be what? 100, because this is 100 here. So since that's 100, this has to be 100 up here, so that makes this piece 30. Because 100 minus the 70.
So that whole thing,
so yep, this has to be 80.
so does that whole bottom one, that whole line has to be 180, right?
Down here?
Yeah.
Yeah. These three do have to add up to 180 because that's a straight line. Yep. Now this one's pretty simple because we got 70 here, so this one has to be 70 and 70, 110 and 110. So all that's left are the angles here. We have a triangle as 50 and 30. This has to be 100 because those three have to add up to 180. And once we have that one's 100, this is 80, 80, and 100. Now, I didn't ask you to name all those angles, but we found them all. Now, is there any one of those angles, any specific one you want me to go back and look at again to show you how we found it?
The top one.
Is there a number off the sheet?
No. I'll find the 30 in that triangle.
This one here or this one?
Both of those.
You got to find this one first.
Yeah.
And that one comes from, you know that if this here is 100, this given, this from here to here has to be 100. So you just subtract the 70, so that's got to be 30. And then those two got to be the same because they're vertical angles. Any other questions on those? Now, obviously, the numbers I put in here, again, are slightly different from your tests, but okay, any questions on anything else off the test you want me to look at? Okay, what you got? Number 20, okay. You're gonna make me draw that sucker, aren't you? Why not? Okay. I got a little tilted, but it'll work. So 20, what we're asking is if IB equals 6. So IB is this right here. That equals 6. If DJ so this is DJ here is 2, so that's 2. And CJ, so this is C, CJ is 4. Find EJ, this is E here. So what we're looking for is this length from here to here. We have intersecting chords, so if we knew this length here, it would be 2 times that length equals 4 times, if I call that x, it would be 4 times x, right? Do I know this length?
Yep.
Yes. How much is it?
4.
Careful. All the way across, I gotta go. So you got double the 6. You get a diameter of 12. 2 minus 2 from the 12 is 10. So then 2 times 10 equals 4 times x. Does that make sense? Because if you have a triangle, or a circle, and you got 2 chords that intersect, when you multiply the 2 pieces of one chord, it has to equal the same as the product of the 2 pieces of the other chord.
That's how I got it.
Any other questions? There's a lot of little rules that kind of converge on one problem, aren't they?
D on the first page.
D on the first page.
That whole thing needs to equal 360, right?
Which number is that? 11?
Find the indicated angles.
Yep. Yeah, you can assume a full circle is 360. Yeah. Any others? Okay, if you need a little more time to finish up, feel free to take it. You can either hand them in today before you leave, or you can hand them in tomorrow if you need to take them home and polish them up a little bit. Today we start our 4th unit of the semester, and this is where we start to get into the nuts and bolts of trig. A lot of people think trig is about triangles, and that's because trigonometry is most often applied to triangles, but it isn't about triangles. All this stuff we've just did with circles is actually the basis of trigonometry. And trigonometry is about describing features of a circle. A line that cuts through the circle, what is that called? Can you guys remember? A chord is within the circle. Secant. Secant, yep. So a secant contains a chord. This is a chord that's in here, but the secant continues to cut through the circle at least one end. A line that touches the circle at exactly one point, but never actually enters into the circle is called what? A tangent. Now, there's something called a reference diameter. Remember, a diameter is a chord that contains the center of the circle. A reference diameter is usually the horizontal diameter. So the reference diameter, if you're talking about navigation, it's east to west. Now, pretend that one I drew in there is horizontal. I got it slanted for some reason, but that should be horizontal in there. So then a sine, which is something we mentioned, I think, once last semester. A sine is the distance from any point on the circle to the reference diameter. So every point on the circle has a different sine. So if I pick this point on the circle, its sine looks like that. Now distance is always measured in a perpendicular. So that's a sine. If I pick this point on the circle, its sine is that, right there. It's from any point on the circle to the reference diameter. I always say it's a distance because it always has to hit at a perpendicular. But technically the sine is that little line segment itself. The length of the sine is an important value. That is one of our trig functions. But any point on the circle to that reference diameter at a perpendicular is the sine itself.
On the circle to the distance from any point on the circle to the diameter.
The reference diameter. So yes, it's the distance from any point on the circle to that reference diameter. So with these features defined, we're going to define something called a unit circle. And a unit circle is just a circle with a radius of 1 unit. Whether that's an inch or a centimeter or whatever, we don't know. It's just 1 unit. So I'm going to create a reference diameter on this circle. Then I'm going to create a vertical diameter as well. Sometimes referred to as the vertical reference, but the main reason I am doing a horizontal and vertical is I want to create a perpendicular. Obviously, vertical is always perpendicular to horizontal. This point right here is the beginning point. We refer to it as 0 degrees, or it's the east direction. And the reason we've been talking about arcs and degrees of an arc is on the unit circle, we actually travel around the circumference of the circle in an arc. So let's say I pick a point right here. That arc that is formed from 0 to there has a certain number of degrees to it. That point is referenced off of the size of that arc. So let's say that arc, and then you're going to have to get used to some notation here. Theta, the Greek letter theta, is just a variable that refers to any generic angle. Just like we'll use x for the length of a side or whatever, theta is the size of an angle. Now, some of the packets we use will use a or b or x or whatever for those angles as well, instead of getting into the Greek letters. But that, let's say that arc is theta degrees. Just like saying x degrees or whatever. So what that means is if I connect this, if I draw the radius from the center of my circle out to that point, this angle in here is also theta degrees. Theta is what we call a reference angle as well. What I mean by reference angle, it is an angle between this piece here is what is called a terminal side. If we think of that angle as being a rotation, 0 degrees is the initial side. And we rotate to the other side, the terminal side. So it's saying we start at 0 degrees and we rotate to that other side, that terminal side. So we start here and we end here. The sine of that point on the circle, right here, that length is defined to be the sine of theta. Abbreviated SIN, we drop the E. That is the first of our major trig functions. Next, if I take this radius here and I extend it out through the circle, I've created what feature of a circle? A line that cuts through the circle is a secant. So what I've created there is a secant. The question is, where do I stop the secant? Well, we're going to create another feature here that touches the circle at the reference diameter. That's a tangent. Very good. So what we have here is the distance from the center of the circle to the point where these two intersect out here is the secant of that angle, secant of theta. The distance from that intersection to the reference diameter is the tangent of theta. So we have the sine, we just found the secant, and the tangent. Those are actually the three basic trig functions. Now the problem is we're not usually taught secant when we're learning trig. We're usually taught sine, tangent, and cosine. So what's the cosine and how does it fit into all this? Well, cosine is just the word sine with a prefix on it. So what does that prefix co, CO stand for? Actually, co means of the complement. So the cosine of an angle is asking, let's say if I ask for the cosine of 30 degrees. What that is asking for is the sine of, what's the complement of 30? 60 degrees. Now let's go back up to our unit circle here for a minute. Where is the complement of theta here? Well, this angle right here, this is a right angle. This is 90 degrees here. So the complement of theta would be right here. Does that make sense? So what that does is, if that's the angle we're looking at, we would use this vertical reference. And this right here would be the sine of that complementary angle. That length right there is the cosine of theta. Now, most of the time, rather than looking at the cosine being up there, we look at the cosine down here. The reason we can look at the cosine down there, of course, is this is a rectangle And opposite sides of a rectangle are equal, so this side's going to be the same as this one down here. Because of certain relationships that we're going to see in a little bit, we tend to use the cosine rather than the secant. But the cosine and the secant are actually very, very closely related. Any questions so far? So what we've got here is we formed two triangles. The first triangle we formed is this one right here. This little one. It is completely inside the circle, so none of its sides can be longer than 1, because remember, the radius of this circle is 1 unit. So this here's my angle theta, and this is the radius of the circle here. This hypotenuse is the radius of the circle, so that's 1. Does that make sense?
What do you have written up straight above that triangle?
Here? That's the, remember we talked about the cosine? The co means of the complement. So the cosine of an angle is really asking what's the sine of the complement of that angle. So when we ask for the cosine of 30, what we're asking for is the sine of the complement of 30 is 60.
Either one will be the same.
It should be the same, yes. If two angles are complements, the sine of one will equal the cosine of the other. Now, because this is a right triangle, if I draw another right triangle, of course, there's one angle that's always going to be the same. But if this angle here is the same as that one, then, of course, the third angle has to be the same. Because in triangles, if two angles are the same, the third one has to be the same. This, of course, is the hypotenuse. Right? This is the angle we're looking at. So what we're going to do is we have two legs here. We're going to call this one the adjacent leg. It's the adjacent leg because it touches the angle that we're looking at. Good question. That's right where I was going. This is the angle we're looking at. This leg touches that angle, so it's adjacent to it.
Like you just established that today or something.
This angle over here. Okay, so this leg over here is across. It's the opposite leg. Because it is across the triangle form. It does not touch it. It is opposite that angle. Now, if you remember from our unit circle up here, from that triangle, this side is the sine and this side is the cosine. So this here is the sine of theta. This is the cosine of theta. So if I want to find the sine of theta, if I know that value of sine, right, that angle, and I'm looking in this triangle here, the opposite leg corresponds to the sine of theta. So I'll put the opposite. I'm going to just abbreviate OPP over here, opposite. I know that the hypotenuse of this triangle is 1, and that corresponds to which side over here? The hypotenuse, right? This side and this side correspond. So let's do the hypotenuse. The sine of theta is equal to the opposite side of this triangle over the hypotenuse of this triangle. It's the sine of theta over 1, technically, because the hypotenuse of this triangle is 1, because it came out of the unit circle. So I'm sure most of you, if you've had any sort of trig, you've seen that sine is equal to opposite over hypotenuse. Well, that's why it's defined that way. That's where it comes from. If I want to look at the cosine here, the cosine of theta, and I'm going to compare that also with its hypotenuse. On this triangle over here, what side corresponds with the cosine? The adjacent leg. So I'm going to abbreviate that ADJ, adjacent. Over, and of course the 1 still corresponds to the hypotenuse. So So the cosine of theta is equal to the cosine of theta is equal to the adjacent leg over the hypotenuse. Notice I didn't put any links into this triangle yet, because all right triangles, if they have that one angle that's equal to theta, the sides are going to be proportional. It's going to be similar. So there's sine and cosine. We haven't identified tangent yet, because tangent comes from a different triangle. Tangent comes from this bigger triangle here. So let's pull this one out. Now looking at that triangle, one of the sides of this triangle is still equal to the radius of the circle. It's this bottom side down here is the radius of the circle. You see it? So that side's going to be how long? 1. So if I come down here, this is still theta. This side is 1 unit because it's the radius of the circle. This side was the tangent of theta, and this is the secant of theta. So once again, looking at this triangle, where this is theta, so it's similar. This is the adjacent side. This is the opposite side. This is the hypotenuse. The tangent, I would do tangent and 1 because those are the tangent's the side I'm looking at and 1 is the side I have. In the other triangle over here, which side corresponds to the tangent? The opposite, right? Then I have the 1. Which side over here corresponds to the 1? The adjacent. So the tangent of an angle is equal to the length of the opposite side divided by the length of the adjacent side. Let's look at secant. No, you don't, but I'll show you how to work it in a little bit. So the secant corresponds to what side in the other triangle? The hypotenuse, right? And the 1 still corresponds to the adjacent side. So the secant of an angle is equal to the hypotenuse over the adjacent. Now if I scroll up just a little bit, do you see a similarity anywhere between the secant and another trig function? Cosine is adjacent over hypotenuse. Yeah, the secant is hypotenuse over adjacent. So the secant is the reciprocal of the cosine. And I'll show you what that means on your calculator when I try to calculate secant after a while. So what we have here so far, sine of an angle is the length of the opposite side over the hypotenuse. Cosine of an angle is the length of the adjacent side over the hypotenuse. Tangent of an angle is equal to the opposite side over the adjacent side. This part here, if many of you use the mnemonic, SOHCAHTOA, that's where it comes from, right there. SOHCAHTA or TOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent.
When would we have done this?
This would have been junior or senior level high school. Algebra 2 or pre-calc?
I remember that from school.
Okay. The trig functions you're probably not familiar with. We define the secant over here as hypotenuse over adjacent. I didn't draw the triangles in because my circle was getting cluttered, so I'm just going to give you these. The cosecant, that's cosecant, is what that stands for, is equal to the hypotenuse divided by over the opposite side. And the cotangent, that stands for cotangent, of an angle is the adjacent side over the opposite side. Now you can see these come in pairs. The sine and the cosecant are reciprocals. Sine is opposite over hypotenuse. Cosecant is hypotenuse over opposite. The cosine and the secant come in pairs. Cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. Tangent and cotangent are pairs. Tangent is opposite over adjacent. Cotangent is adjacent over opposite. There are going to be a lot of relationships between these angles that we're going to look at as we go on. For now, let's look at how do you calculate these in your calculator. Most of you, it looks like all of you have a two-line display calculator, which means you'll actually enter it as it appears. Some of your cell phones use a little bit of a reverse logic called RPN. What you have to do is you'd have to enter the angle first. Well, let's say we are asked to find the sine of 30 degrees. Most of you on your calculator type in sine and then 30. You should get 0.5. So give that a shot and make sure that works out for you. Got it to work out? Okay. So sine of 30 degrees. If you need to find cosine of 30 degrees, same thing. Press cosine, enter 30 and hit equals. Should be rounded off to 0.866.
So it's really the sine of 60.
If you did the sine of 60, you'd get the same thing, yes. That's a good point. I'm going to write that down here because the cosine of 30 degrees is the same as the sine of its complement, so sine of 60. So do sine of 30, you get sine of 30, and enter. Tangent of 30. What do you get? 0.577. So let's look at some of those functions that we don't have on the calculator. Secant of 30 degrees. Now we said secant is the reciprocal of cosine. Most of you have a key on your calculator that looks like this, x negative 1. Or you'd have x 1 over x like this, one of those two keys. Most of it should be an x negative 1. So what you have to do to find the secant of 30 degrees is this. So you find cosine of 30 and hit equals. And then you hit that reciprocal key, x negative 1, and hit equals. I believe it's like 1.15. Did you find it on yours, Hannah?
So for that's secant?
That's for secant. Secant is going to be cosine and then reciprocal. So you've got, nope, where is it? Right there, x negative 1. So you would do cosine 30, hit equals, then x negative 1 equals. Thank you. The cosecant of 30, yeah.
So mine is somewhere normal sine button.
Then the sine negative 1, that's actually the inverse sign. So it's not the reciprocal of sine. That's if you're given the 0.5 and you use that key, it'll give you back the 30 degrees. So now for the cosecant of 30 degrees, cosecant is the reciprocal of the sine. So you find the sine of 30 degrees, hit equals, and use that reciprocal key again. Should give you 2.
The cosecant.
Cosecant.
When we go over cosecant.
All I did is I put it up here. We just put it up here. It was just in our list. Remember, it's linked with the sine. Hypotenuse over opposite.
Okay, I'm finding the cosecant.
You do the sine. So we're doing the cosecant of 30. You do the sine of 30. Hit equals. Then use that reciprocal key, the x negative 1 key. You should get 2. Now the cosecant of 30, by the way, is going to be the same as the secant of 60. Because cosecant means the secant of the complement.
So cosecant.
There's a lot of relationships here. It's going to take a while to get used to them.
Cosecant is a reciprocal sine.
Yes. For now, that's the big part, is know that to find the cosecant, you find the sine and you hit that x negative 1 key, the reciprocal key. So cotangent is the reciprocal of the tangent. So to find the cotangent of 30, we find the tangent of 30, hit equals, then use that reciprocal key. So tangent.
The reciprocal of tangent.
Yep. So you type in tangent 30, hit equals, use your reciprocal key, 1.732. Now, of course, the cotangent is going to be, the cotangent of 30 will be the same as the tangent of 60 degrees. Because, again, it is a cofunction. Tangent of 30, hit equals, and then x negative 1.
So that's it now, right?
Now you got to hit the x negative 1 and hit equals again. That's it. Those are the 6 functions. So let's try it for a different angle. And yes, I chose 60 degrees on purpose here. Sine of 60 degrees. Now let's scroll back up here before you punch this in. Cosine of 30 degrees is 0.866. Remember, cosine is asking for the sine of the complement. So the complement would be 60 degrees. So the sine of 60 better be 0.866. Go ahead and punch that in and see what you get. You get the 0.866. Good. The cosine of 60, you're just going to hit cosine in 60, is going to be 0.5. That's the same as the sine of 30. Tangent of 60. So 1.732, the same as the cotangent of 30, right? So now the next step, secant of 60. What's our keystrokes? What trig function is secant related to? Cosine. So it's the cosine of 60, hit equals, then x negative 1, hit equals again, and we get 2. Notice that's the cosecant of 30, the relationship there. So now the cosecant of 60, what function is cosecant related to? Sine. So you find the sine of 60, hit equals x negative 1, and then equals again 1.15. And finally, cotangent of 60, tangent. Yes, your tangent of 60, hit equals, and then reciprocal. Same as the tangent of 30. Yeah. Cotangent 60 is the same as the tangent of 30. 0.577. Okay.
Chill, man. Chill on it, bro.
No, you had the right idea. You knew what I knew what you were thinking. You just connected it the wrong way. Okay, there's going to be a packet I'm going to give you here in just a minute. And in this packet, Page 338 to 341. We're looking at 1 through 73, the odds. Now again, I realize that's 37 problems, so do a few, skip to the next section, and then make sure you understand each section. Because as you go up through here, each section is going to have slightly different styles. Some sections you're going to have to use this reciprocal key to find the function, and other sections you're just looking for the function.
How do you do it without a calculator?
If you were to do this without a calculator, you'd have to use tables. And the tables actually literally have the functions listed out for every angle. Some of them down to the like 30 or 15 minutes of the angle. I've seen them listed down that far. The thing is, they would only list sine, cosine, and tangent. So you'd have to then do 1 divided by that number to get the cotangent or cosine or cosecant. Or not cosine, but secant and cosecant stuff. But yeah, doing these without a calculator was extremely tedious work. You'd have to have I've actually got a book. I don't know if I still have it in my office or if I have it at home. It was a book of tables, and it's like 300 pages of trig tables and logarithm tables and stuff like that are math tables. I've never actually used it because I grew up in the age of the calculator, and it just makes you appreciate what the calculator does for you. I'm going to hand out that packet for you. You guys going to see Carter, hopefully see Carter today?
Yeah.
Willing to try to give him one?
I'll give it to me, buddy.
Okay.
No.
Yeah.
After a chance to meet, buddy.
Yeah.
I was over 2. Okay, you need.
Oh, Carter does?
Yeah.
Oh, he's having some issues?
I don't know.
Okay. If you see him, tell him I'm free at activity hour day, 11:30 to 12:30. 11:30 to 12:30. I've got to run down to the auto shop at some point, but I should run into him on the way there if he's trying to track me down.